Diciamo questo no, no, non c'è un quasi nessun altro. Sono fatto 6, 7, 14. Ok, cominciamo fra 2 minuti. Prego tutti quelli che sono online di spegnere il loro microfono. Innanzitutto subito di confermarmi se vedono lo schermo e se la voce si sente bene. Senti il microfono. Viola ha detto che senti.
Trial.
Mi confermate ragazzi che sentite? Sì, perfetto.
Trial.
Ciao. Ciao.
Trial.
Andrea, Andrea Barone. Archivari. Ok, era Andrea Barone. Ok, dai. Dimitrios Tsoulis with professional consultancy, professionisti in grandi, fatte con geology and science engineering, okay, and the Aristotle University of Thessaloniki. Dimitrios Tsoulis is now working with us several years. We are working together also from editorial point of view, because we were both of geophysical perspective, which and now we are working on a project involving satellite, new satellite measuring. Is projecting in any case, this satellite is projected with a new approach, which makes very normally and Professor Tsoulis has worked
mainly on geography, but in the author of this very important study, so we invited him to a talk. Thank you very much for presenting. Very happy, very honored. And, it's talk I present of the significance of the terrain crustal data of global to the topic of the modeling. So this is an overview talk which I would like to start by the overview. So these bullets are saying structure, say the pillars of this discussion, which one we also see as the bullets of research. So on the one hand, we have the actuality of the Earth's dynamic system. The Earth is changing, its geometry is changing, its gravity is changing. So for these Earth systems, of course, we introduce different sources, different sensors, and different data. So on the one hand, we have high resolution data, both for the Earth's shape, but also for the geometry. So these two elements, of course, geometry, property, gravity, is one of the two main pillars of how to describe, how to model this dynamic Earth system and all its phenomena. The other pillar is what's the organization of this data? On one hand, geometry represents for global crustal models that describe very very detailed crust, its structure, topography, the open surface, the upper boundary surface, but also the ocean bottom, the ocean overview. And we have temporality models that give the dynamic component. And these are gravity models for big family units, both from satellite or from combined solutions. We have all these dedicated gravity satellites, satellite missions, which have been taught in few minutes, and they produce the main part of the Earth's gravity formation we know today. Of course, we go on to combine the information with the rest of the data and other things. One important pillar is modeling. From this situation, we are in a good position that we are able to reproduce different procedures because we have the data, we have the modeling, we have the theory, and we can reproduce and we can go on and really introduce higher and more detailed scales for this phenomenon. And finally, interpretation. And of course, everyone is one of the main topics to understand. And this is a big question to link this theoretical model. It is a very nice interplay between how this data fit the available theory, but also how the theory can be expanded, can be adapted to fit in better to this data. So I consider these bullets not only my talk, but also interesting thinking about the big challenges today, all the abundance of this data set, how to navigate towards the understanding and the better exploitation of this data. Okay, let me start by talking about geometry. Okay, on the arc, we have one big category of data sets describing the geometry. these are global data sets for continents. These are satellites that go around the globe and they scan with typical radar techniques or laser techniques the surface where these beams can be reflected upon. So you see the result of this kind of data stops at the ocean, because of course either they stop there, so here this big family of geometry that corresponds only to the continents, or specific reflecting surfaces such as ice. But unfortunately, this information stops at the oceans. You have to decide what is the reflecting surface. For the oceans, we have another completely sometimes, of course, operating information, the altimeter, the satellites that are specifically designed for the water surface as the reflecting surface. Then get another completely different information about sea level itself, another job. But interesting is that we need
we have to switch to microphone. People say that online we're just work the mic. Okay, go ahead, but I will switch the microphone and the microphone will now be here.
Yes.
Okay. So let's try. Sorry, but people online say that microphone is not working. Okay. So I will switch the mic.
Okay, that's it.
Okay, now, okay, I see that my voice now will be heard, perhaps.
I don't know if it is better than this, but
But
let's
also
say,
the transparency change doesn't.
okay. Yeah, but because I have to move the
sorry.
pointer here, yeah, now sure.
Now it's working. Okay, so let's hope that this problem is solved. Okay, we have now this particular information, and then interestingly and important for us is, of course, we do not want that this information is interrupted. And of course, the surface of the continents is the upper surface of the crust, and it continues in the bottom of the oceans. How do we get this information to the bottom of the ocean so that we can add it to the previous one of the scanning of the Earth's surface? Here we use altimetry indeed. Here we use the information that we can measure, and we infer from this information the surface that we cannot measure, which is the bottom of the ocean. We use the altimetry data and we do some inverse modeling to estimate the surface of the oceans. And if we combine these two data sets, the structure of the surface of the oceans from altimetry data, from the analysis of altimetry data, with the open surface reflection information satellite, to produce this family of data sets, which is, let's say, the upper boundary of crust in a global scale. This is an important information because now we have completed the description of this surface without any holes, without any discontinuities. Okay, and now for gravity. For gravity, we have another group of family of applications that have all their origin in the introduction of the GPS positioning system. The fact that we have an operating system, satellite positioning system for every point in three-dimensional space until the beginning of the 90s gave the emergence of the idea, okay, if we have this system of satellites that provides us continuously with information of positioning, okay, why don't we use the GPS receiver as an onboard instrument satellite that will independently make his own orbit in a much lower height than GPS. And this is actually what gave this really opening for all these techniques that we say in different names, satellite to satellite low satellite to satellite tracking, high-low satellite to satellite tracking, satellite gravity graviometry, different names, but actually take this availability here, it's based on this availability, that we can track the satellite orbit very accurately, very continuously, again with no gaps, for any satellite we push at any level, as long as it is less than 20,000 kilometers. So these three types of dedicated gravity satellite missions is how we call them, because they are dedicated in terms that, of course, these satellites can also measure other stuff like atmosphere, magnetic field, the consistency of the Earth's layers, the atmospheric layers, but also what here in this discussion I would like to point out their application on gravity, the information of the gravity. And what do exactly, how does this information emerge from the satellite data? Well, again, the basis is here, these two equations, which are the couple of equations that express the background of the analysis of this data. What's the story here? It's what we call spherical harmonic analysis and spherical harmonic synthesis. Very simply said, the fact that if you have a set of coefficients, which we call spherical harmonic coefficients, and these coefficients are known up to a specific maximum degree and order of expansion. So we have these numbers, you insert them in this double summation, and this summation gives you the functional function that is defined on the sphere at every specific point on the sphere in the fourth and fifth dimensional space you desire. If this function is the potential, in our case, these are called potential harmonic coefficients. So these are the coefficients that describe, in that case, if the function here is potential, the gravity field here. And inversely, the analysis, and this is called synthesis, by the way, the analysis is the opposite, to compute these coefficients by starting from the information we have of the potential. We get this information by analyzing the satellite orbits, the satellite movements. So from analyzing the orbit of the satellite and focusing on its discrepancies, on its differences with respect to a regular canonical Kepler-wise orbit, you take these residuals and you somehow in mathematical modeling, you put them, these discrepancies against the satellite, the spherical harmonic coefficients that define this discrepancy. So this would say someone that this is the basis of the analysis of all these models in the computation. So what do we say, what do we mean by global gravity models then in this sense? We mean sets of spherical harmonic coefficients of this manner that are linked to the gravitational potential function of the Earth's gravitational potential. And depending on the length of the data that is used, the type of data that is used, and the decisions that we make for building the mathematical model for the analysis of this data, we get sets, we get groups, we get matrices of these coefficients up to specific degree and order, which is of course also linked to the methodology used or the length of the data that was incorporated for this computation. This is why from 1966, where the first satellite was set in motion, it was able again to give positions on the surface of the Earth, which led with this very, very sparsely selected position from the first satellite in 1966 on the surface of the Earth, which could lead to a very, very small picture of the Earth's gravity field, a few degree and orders, a few of these coefficients. We find ourselves in the position to say, okay, since 1966, we are well over 180 such models. And if we add daily, weekly, or monthly solutions to that static solutions, we get hundreds or thousands of models that are available. Especially these models are focused on time variable phenomena, time variable events, water cycle, tectonics, and so on. Okay, now I would like to talk about how you can link this geometry on the one hand, these digital terrain models, this geometric information. How can you link this information with gravity? Is it possible? Can it be done? Well, this is what we call topographic isostatic gravity model. So this is a specific category of model of gravity information, of this kind of information, so the coefficients. But these coefficients do not, they also are expressed from some kind of spherical harmonic analysis, because this is the only backbone that is true for every model, but not as input. They don't use as input the movement of satellite or its measurements, but they use as input the geometric information presented to us from global models such as the ones I showed earlier. So global model of terrain and ocean bathymetry. And you see now the significance. We need this, the whole surface. We are not, nothing we do here if we have only fragments of this surface along continents. We want the complete surface, also the depth, the bathymetry information. And here we just apply very standard tools of how to expand the inverse distance function in a series, and we get these coefficients now. It's the same equation as the one I showed before, but we focus ourselves on the coefficients that express these masses. And this we can do arbitrarily. We can use different compensation, as we say, levels, different, let's say, lower surface, because the upper surface is always the visible topography / bathymetry. This is what we have measured. This is what we have as the data. But we can change, of course, the lower limit of this integral. Given, and this is an important requirement, the density distribution. We want to know the masses that are defined inside these two, the lower and the upper surface. And if we integrate, we can get spherical harmonic coefficients expressing gravity of those particular masses. That is, gravity without mantle, without curve here. And this is what topographic isostatic gravity models are all about. So it's, let's say, a mathematically computed gravity model focused only on the effects of the topography, all of this structural information. And okay, this approach needs some kind of compensation. You need some kind of mechanism to describe the balance between crust and mantle, how to define the lower limit, because the upper limit is a given, is an observation. The lower limit should be somehow adhere to some static theory, iron high star, then it minus the flexural resources. Somehow we have to define how this, or we use it directly from a model that is given to us. And we have the attraction component, the compensation component, to get these layers expressed, of course, in the integrations that give the specific contributions to those spherical harmonic coefficients. And now we start to combine this information with the other kind of information. And the first thing that we notice is, okay, the topographic isostatic gravity-related information, the topographic isostatic gravity field, is not dependent on, how often the satellite, how high the satellite is passing. The only requirement, the only quantity that describes the upper boundary, the maximum degree in length, degree in order of this function, the only thing is the resolution of the model. So if the resolution goes up, and it goes up the whole time, you can get really synthetically this information to a very high degree. We have, I present here up to 1,000, but of course, this degree goes up to several thousands if you implement, you use this very dense information we have for the topography. For the oceans, you don't have, of course, the same resolution, and then you can go and artificially make some kind of resolution of to incorporate a better high resolution to, of course, a sparse resolution that we have from the telemetry data from the oceans. And you see here that the let's say combined model stops somehow. Of course, we have here also much better information right now, picture 96, but in any case, they do not fit. It doesn't fit. The geometry information will always be of much higher resolution than any resolution that can be given at the present moment, at least through satellite data. And it's an interesting exercise to see if you apply the area compensation, you get this curve compared to the uncompensated topography. If you have the Pratt compensation, you have a completely different image. You start thinking about which compensation is better, up to which degree, and so on. You start thinking of degrees, of bandwidths of this spectrum, and so on. And you start to realize that this is important stuff, because this geometric information can give me higher frequencies that other techniques cannot, and perhaps one could use them combined for the one complementary to the other. And the other kind of information about digital terrain models is crustal terrain models. So the information not only of the Earth's topography and the variations of the visible topography of the upper, as we said, surface of the Earth's crust, but also fragmentation of its layers, again in terms of the digital model, with a unified resolution globally, but at different depths. Each depth describes a specific layer: soft sediments, medium sediments, medium crust, lower crust, and so on. The last surface being, of course, the well-known mode of discontinuity, so the interface, the boundary between crust and mantle. And here now, this information does not go alone in these models. Crust models are called 5.1, crust 2.0, crust 1.0. These are a lot of models that always get 1 millionth degree, always get higher in resolution, not only geometry, but also consistency. So what is given here is the density, and some other seismic information, such as the velocities of compressional and shear waves. So from seismic information, you get this information for all these layered models. And if you take these models, you start really to understand and to make comparisons between gravity and shape. Okay, because you are able to make direct comparisons of existing theories. Here, RFI scanner or other known theories between the models, but also you take each of these layers and compute the gravity spectrum, as we say, the gravity coefficients coming defined from this layered information, and do all sorts of analysis and implementation studies, again, in the framework of isostatic equilibrium. Or you can start implementing other ideas. For instance, this is an idea that compensates masses to a single layer. A very well-known, very interesting and popular approach in potential theory, the spherical layer, which is a mathematical concept, because the mass is always three-dimensional, but of course, the two-dimensional layer can also be assigned to a specific mass. And this is a very interesting thing, because on that layer, you can compensate whatever you want. So you can really take all these three-dimensional things and compensate them to specific layers, compute the same procedure, and interesting stuff are beginning to appear. Interesting structures of the Earth's interior emerge from such approaches. And also, I'm sorry, the possibility to begin to think about bandwidths. Because the good thing about the spectral approach and the fact that you transform all this information into coefficients is that you can cut the summation to whatever degree you desire. And concentrate on that band and quantify medium degrees, medium wavelengths, long wavelengths, short wavelengths, and so on. And of course, you can start evaluating, and the evaluation can be done spectrally. The evaluation can be done in the spectral, in the spatial domain, because we have all this information, all these different sets of coefficients, and you want, of course, a guideline to understand how can we understand these models, how can we validate them? And there are, of course, different available spectral and spatial means to do that. And the other important feature of the coefficient is that you can go to any function that you desire, because the gravitational functionals, the relation between potential, first, second, and higher order derivatives are well known mathematically. Specific eigenfunctions, the eigenvalues, that connect all these functions, so you can just synthetically compute everything from the starting information of the CLF of the coefficients for the potential. And you can go and make, of course, some interesting comparisons in the space domain about geoids or gravity anomalies or gravity gradients between all these models and other available models that you want to understand better. One of the many tools that I'm showing here just for to get your attention is the so-called correlation per degree. Correlation per degree is the amount of correlation between the different data sets and how the high-low SST, the pair, the low SST, the gradiometry models, and the combined models show these very different behavior, show these very different figures. Combined models means models that are also terrestrial data, not only satellite data. And you see that for combined models specifically, you get, well, let's say, the smoother picture in terms of correlation of the different families of gravity models, whereas the other types, okay, they are here the most scattered image of correlation, and the other models similar images. You can start really quantifying this information for the different applications. And another means of quantification is the interesting property that if you have these models, you can translate the contribution of each specific degree in order for each specific bandwidth to a selected function. This you can show in a cumulative manner in dimensional diagram. Again, a very interesting feature that gives you the possibility to quantify specific functionals depending on your application. You are doing gravimetry, you are doing radiometry, you are doing a field survey of a specific functional. Okay, what happens with this information? What exactly is the contribution, let's say here, to the errors in gravity gradient for these different type of models and the differences against some reference? So there are many good properties of the fact that you translate spherical harmonics, and this is one of the important properties in our opinion. The fact that we can get all this layered information and translate it to spherical harmonics is also very important in global scale applications. For instance, I showed before the analysis of some report analysis of the crust 2.0 model. Here, in a more recent publication, is the analysis of the crust 1.0 gravity, which again gives the information that I shown before in a much better, of course, a different level of resolution, different level of approximation. And this is interesting in terms of all the studies that you can imagine of. You can get layer-wise information, quantified information of the gravity scene. It could be geoid height, it could be gravity anomalies, as this picture is, emerging from that specific layer. So like this map, you can imagine, you can find in this publication 7 more or 8 more maps, including also the final, I think I have the next slide, the total effect of the layered information for gravity anomalies. So this is the sediment correction. Here, these are all corrections. Of course, check the color bar. It goes, of course, from 100 milligauss to 400 milligauss. But this is important information because it computes and quantifies all these things that I shown earlier, which is very important for a variety of studies, for a variety of applications, for a very wide length of different applications. And not only that, you can use this information, as I said before. Look, from this information you get, from this analysis, you get a topography produced from these coefficients, which is the left image. And you can compare it with the crust information of the model regarding MOHO depths. Because one of the lessons we learned from isostasy is it always relates to topography. So if the topography has a specific profile, depending on the isostatic model, the bottom of the crust should adhere to a specific route or anti-route to a specific profile. And these models provide this information, provide this lower surface, this MOHO in its continuity surface. And you can start here to very, very specific comparisons about specific isostatic models. And you can go even further. You can go, even since you have this possibility to translate every specific layer to spherical harmonic coefficients, you can go, since you can do the transformation of these masses to spherical harmonic coefficients to a spectral gravity, say, of a part of the complete, of the total gravity signal of the Earth, you can go to different other applications. For instance, one question is the MOHO depth determination. MOHO depth determination can be done by applying the known concept that on the crust mantle interface, there should be some kind of isostatic equilibrium, should be some balance, because if there is no balance, then we would be not standing where we are. Taking this isostatic balance at the MOHO discontinuity and really quantifying it in terms of gravity anomalies, for instance, you can say, okay, in order for this equilibrium to happen, we must have the following equilibrium gravity anomalies emerging from the crust, emerging from the density contrast between crust and mantle at that specific level. But all of these things you can compute. All of these things you can really compute with the story I showed before. So problems like what exactly is MOHO, can we estimate MOHO, these problems now get a very different point of view. People can get this data, and it's certain as a very crucial element in this kind of equations. And indeed, here is a specific application of MOHO inversion using gauge gradients, 7-order derivatives, and crust 1-0 information. And finally, Another part of another specific, again, application is, as I showed here, the elastic thickness estimation. Elastic thickness, again, is a very interesting concept. Not ivory, not pearl, which are, let's say, rigid isostatic models, which present this crust mantle balance in the way the boat is floating on water because of the different densities. These models are due to Henning-Meines. Henning-Meines, a very, very famous geophysicist, who said, okay, why don't we see how the crust bends, how the crust bends because of the load that's upon it. And this load could be, of course, a mountain or some specific mass that we see the physical topography. And then you don't get the rigid model, but you get a more, more curved ones. And these approaches have specific features that the geophysical community knows very well, young modulus and so on. And this information you can get for this crustal data. So this information, the information depending on the bending characteristics of the crust, together with the possibility again to compute contributions of all these layered geometries in terms of gravity, information provides yet another interesting application of computing these surfaces between describing the equilibrium, the balance between crust and mantle, and alternative. Many more applications could be shown here, but I wanted to keep it this short overview. I talked about how global terrain crustal databases provide a detailed structure and consistency of the Earth's shape and interior, because we're not only talking about geometry, we talk about densities, we talk about survey velocities, and so on, other features of these masses. With ever-growing resolution, we get this information always with a better resolution than before. This knowledge enables an accurate evaluation of short wavelength gravity contribution. Now, this short, medium, or this is again another discussion, but the important stuff is that we can really get the different information that we cannot get from any other measurement principle. The spectral representation. The spectral representation permits this geometric information to be given in a manner that can be combined and incorporated for the description of various geological phenomena and geological problems. And another point is interdisciplinarity, because the different sources, the different methods, the different working groups can all benefit from this information, as of course all these research activities show again and again. So this was my talk. I hope I can provide you an overview of this topic. Thank you very much for your attention.
Time for questions, first from the audience here and then from the audience online. We have 6 persons online. Please, over there.
So we have seen different data. Something about the detail of this data, these models. So I can tell you some information you can give.
Well, it's a varied information. There is a rule of thumb that connects the spherical harmonic degrees with what you get in the Earth's surface. For instance, if we talk about the 1 degrees models, so the crust models of 2 degrees, this 1 degrees is 100 times 100 kilometers. So you get a global image of how the crust looks like and its layered structure in this round, of course, very round information. That's why the spherical harmonic degrees of that models go up to 80, 100, 120. They go up to not very high. But if you incorporate geometry, you incorporate these other types of data that show that would increase this number to thousands of thousands, goes much smaller spatial scales. To say that we are in the position that we can completely forget terrestrial information or terrestrial, classical approaches, and we can change everything using only this information is not true. We are not there. Because if we go and, I don't know, define heights or height differences, we still dependent today on leveling data or types of data. But we are already in the position to incorporate, for instance, this kind of global information for GPS in comparison with GPS. GPS leveling is a method that can be already implemented, even for scales relevant to specific applications. But it's always a matter of how high the degree is, the specific model. It's not the answer, of course, very roughly in one word.
Federico.
What are the perspectives of combining successfully all the satellite data center, creating data center, shipboard, on land, airborne? The question is maybe stupid, but maybe very often we don't start to find land, shipboard, airborne, data center. In some languages, but very often it is difficult to merge successfully these two classes of data. What are the perspectives of doing this good results?
Fantastic question. This is a very good question, and this is okay. The 1 million question to say, because exactly what you pose here is the matter of discussion. The merging in terms of theory or the merging in terms of applications, you have to differentiate between the two. The theory seems to me a little bit more complicated, but feasible. But the practical point of view, we do it already. Already now we are applying it because we already know that we will get, as we say, the long wavelength information of the field. So in terms of the Earth, let's say what the kernel in the mantle produces, we get that pretty accurately as evolved from these models. What is interesting is what happens with the higher frequencies. The higher frequencies can, of course, be more and more better explained, better described. We do that already. When we always compute different contributions of the long wavelength, the short wavelength part, so that we can get this one contribution from this information and other contribution for the gravity that we go and measure on site, which is indispensable. Because however good this information is, one gravimeter measures what happens at that point, at that specific time. Because you cannot, of course, define again and again this gravity solution, but you don't have a real-time response to them. Always you have a specific fingerprint, a specific image of that specific period of data that we have used. But you know very well that gravity changes, right? It's not stable. Yes, earthquakes, landslides, everything, all of these tectonic features, tectonic phenomena change the gravity signal. So I don't think that we will ever, forget about the local information. Local information is indispensable. But the question of how to optimally combine and implement and utilize all this information is Very, very interesting question.
Yes. Thank you for your talk. And actually, two questions. The first one is about the difference in the spectrum that you have shown, considering the different composition models to compute the so, yeah, considering that from ready data, we generally estimated the relation of the elastic thickness. So I wonder how we consider different composition models at regional scale instead of global scale. So they make it more feasible with respect to the variation of the morphology and topography. And the second one is about the difference in the maximum spherical that we can reach, considering the breadth data, and instead of using all the breadth data, because actually we have to not the very system, but sometimes the breadth effect of topography is used to compute, let's say, by removing the effect of topography, but sometimes we feel that the resolution of the data is very, very good. So sometimes we improve the resolution model to be so we have other things instead of removing.
Could you please recap a little bit the question before answering? Because
Of course.
it was not heard online.
The first part of the question was, the
Compensation, different compensation.
the different compensation models in terms of regions, different regions. And the question was, or the proposal was, why don't you differentiate between different tectonic sets in Africa, America, so that because it's possible that different compensation signatures may apply. And the answer is yes. And indeed, when the isostatic studies happen, they are always, or the most of the time, tailored to specific tectonic settings. So I can answer to that affirmatively. It happens. This is how one proceeds. That is true. Exactly because all these models show that in some parts of the world, a specific model is nearer to the closer to reality. Somewhere else, some other isostatic mechanism applies better. So always, it is not again a question. Perhaps we can leave it to the next. Could we find a global homogeneous and universally applied isostatic mechanism? Probably not, because it's all of these effects are completely different, and the locality is, of course, what you propose is what happens. This is how to proceed. The other question was about the the role of the topography in terms of higher degree. Yeah.
Actually, it's how to use the topography
on other planets. Yes, it's planetology. Of course, this is what I also forgot to mention. Of course, a lot of things. Perhaps you know that there's a big now discussion about the lunar gravity. There's a big discussion because of these missions. There's a big discussion and has been ongoing for Venus gravity, for Mars gravity, where, of course, we don't have surface measurements. We have not been there, or well, we have been, but and of course the scanning, the laser, and the geometry is the only thing that we have. And the answer to that, exactly because of this kind of background, we are able to use only that for the topography. For the gravity of these planets, and we are doing that. And what we are doing, we start to go inversely thinking, okay, because I cannot put my step on that, how can I infer what could be happening below with some approximations, some assumptions, and so on. So yes, it is happening. And of course, there it is as you said, the forward information that we have which we use to compute the gravity. If we were using that approach on the Earth, of course, we would have to subtract some reference model, to make this work, to make this computation be, some realistic picture of the actual gravity, not of the gravity of the masses only. So a similar thing happens to that planet Jupiter. So you make some assumption of what is going inside in order to infer from this forward computation so it's not like it is a forward computation that cannot lead to the gravity. Not at all. It can lead to the gravity if we take some other assumption of what is going totally for this body in terms of its interior.
See, for example, I'm thinking about gravity,
Yes.
where we have gravity data in the actual model. So we can estimate the topography.
Gravity is again satellite-based.
Yeah, it's Aristotle, yeah. But the two models, gravity model and topographic model, have very different resolution. Of course. So to subtract the effect of gravity to topography to the gravity data.
No, I was not talking about that. I was talking about
My question is, can I consider, for example, the maximum resolution of a gravity model, let's say 80 degrees,
yes.
to truncate, to stop the expansion of the topographic model as well as the resolution, or
These are two different things. No, the topography always, it depends, of course, on the compensation level. It depends how you compute it. But if, for instance, here I was showing, crust-based topography. So the mass, the topographic masses up to a very, very small depth of a few tens of kilometers with respect to 6,700 kilometers of the Earth's radius. So this is a very, very small percent. So I was talking about crust here, even though. But you can use whatever radius you want. So the answer is depending on how you compute this topography related to gravity, you have a different answer every time to your question.
Maurizio. Let's start with Dimitrios, interesting discussion. Let's go to know separation in bands, frequency damping, efficient bands. Because so my experience in normal place, place and length, that many geological surveys cannot be affected with just one selection plan. So what's your opinion when you talking before layers, which corresponds exactly to some coefficients?
Another excellent question, because unfortunately or fortunately, gravity is always the summation of all different things. So it is not, I've shown and I've talked about bandwidths, saying that is a possibility that offers us these tools, not by any means a solution now that we have discovered, but we can really go and isolate everything. No, if I make that statement, I didn't want to say that. But what can be done again, because the answer being you cannot separate so easily. It's not possible. But what you can do is by means of homogeneous and likely family-like models, you can do things to understand if you have applied the same procedure, if you have applied the same mathematical, parameterization of the problem. Because what I have not talked, of course, are the details of this analysis, which are really very sophisticated and detailed mathematical models. So if you keep some things the same, then you could, with a good feeling, draw some conclusions depending on what these bandwidths, how these bandwidths could be, represented. But no, we cannot, unfortunately, use really strictly speaking bandwidths when separating or when localizing interior sources. This would happen, but it's not possible. Yes. At least in a strict sense. Yeah. But perhaps one young researcher finds it.
Very advantage for experts for requested. We can think about the witness GGM plus 2013 global center
Yes.
for land investigation, wave investigation, area size, the 100 kilometers.
What would you like to know? It would be a good selection between. It's a good solution.
I found these the same. The blue,
Yeah.
here plus
Yeah.
20.
Yeah.
And this very good data set also for local investigation. But we found that there is a strong correlation with the ball. So that
Okay, this is the answer. The answer not only for that model, but for any model that may or may not be used or is available, is that always, at least in my sense, in my understanding, is a matter of local validation. So this step is independently of how, because in order to assess this kind of models, we do similar processes like that, which are global, which are spectrally defined and spectrally observed from spectral point of view, and we draw different conclusions saying, okay, this is the specific level of agreement with respect to some other model. But the part where you go and evaluate and assess this model locally is again indispensable, which deals with the characteristics of the area. A specific model could perform in a different way in different locations because of the characteristics of that specific region. So this is again a matter of implementation and link with local information, which is always what we also do. In terms, you cannot use it because we are thinking always in terms of some automatisms, so something that can be automated. This is not the case. When you go and try to couple, to close this information, this global information with local information, you need also local observations. Of course, if you want higher accuracies, if you really want to go to centimeter or even less, of course you need local data.
Any other question from the audience? If yes, please open your microphone and speak. Otherwise, we can perhaps thank again our guest for his seminar, and thank you for attending the seminar. Okay, and that's it. Thank you all also online for attending the seminar. Thanks a lot.
Thank you very much.